see in blue are the dams that are currently under construction. And the red ones are dams that are in the books, on the books, to be finished or built by the year 2030. And so what you see here is, of course, a huge amount of dams. In fact, all the dams together here, it's over 3,000. It's close to 4,000 new dams that are being built or will be built shortly. And so if you look at it, you see again a very wide geographical spread, but clearly the dams that are being built now are being built in different places than they used to be built last century. For instance, if you look at the United States, there's no new dams being built in the continental US. There's a couple in Alaska. In fact, some of the dams in the US are being commissioned by now. And you see, for instance, a lot of activity in South America, certainly in Brazil, but also in Paraguay, in Argentina. And what's most remarkable is this string of dams here that runs from Central America all the way to the tip of South America, and that essentially follows the Andes Mountains. So these are dams that are being built at high altitude in the Andes to capture the headwaters from the Andes. Those dams are no longer for flood control or water storage. They're really hydroelectric dams, right? Essentially to produce electricity for the economies, the regional economies. If you look at Africa, for instance, there's very little going on in the southern part of Africa, but you see a lot of dam building in the central part of Africa. A lot of these dams are actually being financed by Chinese entrepreneurs. And again, still there's a lot of activity in Turkey. You see a lot of a big string of dams here along the Adriatic Ocean. And then here, again, as for the Andes, you see this string of dams being built up in the Himalayas. Again, for hydroelectricity production, again, at fairly high altitude. And now if you go to China, a lot of dam building is still going on in China, but it's no longer in the eastern part of the country, it's in the western part. So we're moving up again in altitude to the plateaus in Yunnan province and the Tibetan plateaus. So again, you see this tendency for dam construction to move up into altitude away from the floodplains. The only exception is this string of dams here. That's the Mekong River. And in fact, the Mekong starts off in China, runs to Laos, Cambodia, Vietnam. In all of these countries, practically all the tributaries of the Mekong River, there's extensive dam building going on. In fact, I had a chance to visit in Laos one of these tributaries. What you find now is these cascades of dams. So you go up the tributary, you have a first dam being built by the Germans, second dam built by the French, and by the Chinese, etc., etc. So you get these cascades of dams. Most of them, again, for production of electricity. Right? So you see a very different picture for the second wave of dam construction than we saw for the first wave of dam construction. In fact, if by 2030 all these dams are indeed constructed and completed, some of them will never be built. There's a couple that already have been scrapped in Brazil, for instance. But if all of these dams would be built, or most of them will be built, then by 2030, 90% of all rivers will be fragmented to some extent by dams. Another way to look at that, all these water molecules that are coming out of the mountains and want to go to the oceans, 90% of them will have to pass through one or several dams before reaching the oceans. So I would propose to you that damming is probably the biggest modification of the hydrological cycle, of the freshwater hydrological cycle of the planet. All right, so now, what are the consequences of damming for the river system? Well, the first one is, of course, the hydrology of the river will change. This is a textbook example for the Aswan High Dam in Egypt. What it shows is the average water flow to the Nile before the dam was built. And so the classic thing here is these summer floods that have characterized the Nile for millennia and have actually punctuated the history and the civilization of Egypt. And so after the dam closure, of course, what you see is no more, these floods have completely disappeared. This process is what we call the flow homogenization of the river. So the seasonality is completely gone. Now, one of the consequences of this, which was not expected, is that before the closure of the dam, Egypt had actually a very kind of quite an extensive fisheries. And those were fisheries, coastal fisheries off the coast of Egypt. And so after the dam closure, within a few years, the fisheries basically collapsed. And the reason for that is that by closing the dam, building this Aswan Dam, the nutrients that were transported by the Nile into the nearshore ocean, basically it didn't happen anymore. And the food chain simply collapsed. It's interesting because there's a couple, when this happened, of course, people were didn't know what was happening. There was also a theory that was spread by some of the Egyptian media that it was actually the Israelis that were dumping poison in front of the coastal water of Egypt. But what you see here is already kind of a first link between nutrients and that. So this thing of flow homogenization, here's is a nice little map of the United States. It's a paper by Hoff already a couple years ago, and they developed an index to measure this flow homogenization. So to look at the flow before damming, so the seasonality, and then after damming, the disappearance of the seasonality. And of course, what you see is that over large parts of many of the watersheds in the US, because there's so many dams, you have this flow homogenization. If you look at the title of the paper, it says Homogenization of Regional River Dynamics by Dams and Global Biodiversity Implications. And the idea here is that if you have a river system where you have a highly seasonal flow pattern, well, then the ecology in the river and the flow will adapt to that, right? So the ecosystem is basically adapted to the flow regime, and so some of the organisms will actually have a life cycle that reflects that seasonality. So if you now homogenize the flow, then obviously you're going to make the conditions more favorable for more cosmopolitan species to live. And so in this paper, they don't have a proof of it, but they do speculate that loss of river biodiversity to a certain extent might be linked to this flow homogenization following damming. All right, so now what about the dams and the nutrients? So I usually start off with this simple diagram. It's a very simple diagram. So, but think about a river before the dam. So the landscape or nutrients are being loaded from the landscape into the river, and then the river transports this downstream. Obviously, there are in-stream processes, there are processes in the floodplain that are going to change it, but let's simplify it and just think about the river as kind of a transport pathway of the nutrients from the upstream point of loading to the downstream part of the river system. So now you put a dam on there, and if you do that, you will transform a stretch of the river upstream into the reservoir or into something that's more like a lake, right? So what's going to happen is that the flow velocity here, relative to the initial condition, the flow velocity will slow down, the sediment settles out, the light conditions improve, the residence time of the water in the reservoir will be longer than it was in this river stretch. So all this makes the conditions favorable for the biological machinery to set in, primary production, photosynthesis, biomass production, death of the biomass, remineralization, etc. And so we start having typical cycling of nutrients similar to what we find in lakes. Now, over time, some of the nutrients that are being cycled around here will start being retained or eliminated from the system. And so retention can be, for instance, nutrient elements that are associated with the sediments that are accumulating in the reservoir. This could be, for instance, the case for phosphorus. For nitrogen and for carbon, you can also have release of some of the gaseous species, so CO2 and N2O and nitrogen gas, being essentially eliminated from the system. And what this means is that what you have here is that through retention and elimination, it means that the amount of nutrients that are going to come out of the reservoir will be less than what came in. Right? So this will have implications, of course, for the downstream reaches of the river and also for the receiving water. So that's essentially what we wanted to figure out. So what I'll show you now is, I'll start with an example for an individual reservoir, and then we'll move up ultimately to our global estimations. So the reservoir we've been working on is Lake Diefenbaker. It's one of the largest reservoirs and oldest reservoirs in Canada. It's about 200 kilometers long. There's actually two dams. There's one over here and there's a dam here. But this is the main dam. So most of the outflow is to this dam, the Gardner Dam. So it's on the South Saskatchewan River. There's also a little bit of flow coming into the Swift Current. So the green dots are places where sediment cores were retrieved. So we've analyzed these sediment cores. So we have some of the sedimentary archives. There's also a very extensive water quality monitoring program. So we have a lot of data on this reservoir. So we first started actually looking at silicon. When people talk about nutrients, they often think about nitrogen and phosphorus. But for aquatic ecosystems, silicon is, of course, also a very important nutrient because it's being used by these little algae that we call diatoms, which make these little shells out of silica. So without silica, these diatoms cannot grow. And what I'm showing you here is these heat maps that show the dissolved silicate concentration as a function of time. This is the dates. From upstream to downstream, and in the upper part of the reservoir, the epithelium, and in the bottom part. I'm not going to go to the details here. What I want you to get away from that is that the dissolved silica distributions are very dynamic. They change from upstream, where the river is coming into the reservoir, to downstream. They change a lot as a function of time, and they're different between the epithelium and the hydrology. Most of these dynamics is driven by the biology. It's the uptake of dissolved silica by these diatoms, these little algae, when they build their little shells. And when they die, these little shells redissolve and release the silica back into the water. So you can look at these type of dynamics, and there's quite some interesting information here. But let's look at it in terms of the retention. So the retention of silicate, of dissolved silica, is the difference between what came into the reservoir and what goes out of the reservoir normalized what came in. So 100% retention means that all the silica, dissolved silica, come into the reservoir, stays in the reservoir. 0% means that it's all good and true. And so what you see here, and you look at the blue line, this is essentially this retention as a function of time for 2 years, from June 2013 to June 2014. And you can see that it varies a lot. In addition, if you look at the scale is here, sometimes it's positive and sometimes it's negative. So sometimes more dissolved silica comes out of the reservoir than comes in, and sometimes it's the reverse. And this is completely driven by these diatoms. So if you go, for instance, in June, July, and August, you see positive numbers. Because the dissolved silica comes into the reservoir, the little diatoms utilize it, and therefore there's less dissolved silica going out of the reservoir. But during the winter, you see the reverse, because there's no more diatom growth. They're all dead, and basically their little shells are dissolving, releasing the dissolved silica to the water, and it comes out. So you can see that it is very interesting in terms of the seasonal dynamics, about the biology going on. But what if we now integrate over the year? Well, we've done that, and we've compared what happens to silica, for instance, to what happens to phosphorus and nitrogen. So if you do it now on the annual retention, so you integrate over years, we find that over 80% of all the phosphorus entering the reservoir stays in the reservoir. So it's very efficient trap for phosphorus. About 30% of the silicon gets trapped, and essentially no nitrogen gets retained in the reservoir. So that's where I refer to as when you build a dam on a river, you are not only changing the absolute fluxes of those nutrients, you're also changing the relative fluxes. So the ratios of nutrients coming out of the reservoir will be different from the ratios that came into the reservoir. And so that's a big driver, because it means that the nutrient limitation patterns downstream will be modified once you put in your dam. So that's for one single reservoir. So if we go now to the regional scale, so I'll show you now results for the Lake Winnipeg watershed. Lake Winnipeg is actually a system of two lakes here. There's fairly large lakes. Here, by the way, is Lake Superior, so you can see that Lake Winnipeg is fairly large. The whole watershed is about 1 million square kilometers, so it's a big watershed. In fact, Lake Diefenbaker is somewhere over here. So with these two maps show, so this again is the watershed of Lake Winnipeg, up here and down here. And what it shows for these different reservoirs, so each circle here corresponds to a reservoir, to a dam in the watershed. This shows total phosphorus retention, this shows total nitrogen retention. And so if you take, for instance, this is Lake Diefenbaker is right here. So the size of the circle is proportional to the total amount of phosphorus or nitrogen being retained or eliminated. And the shading is a function of, or is proportional to the retention efficiency. So the darker, the more retention. So what you want to get out of this is that if you look at the shading up here for phosphorus, in general, it's darker than for the shading for nitrogen. So again, what we saw for Lake Diefenbaker specifically, we see is also true for most of the other reservoirs. They're more efficient in trapping phosphorus than trapping nitrogen. In other words, the nitrogen gets through, and the phosphorus tends to be retained. Now, this is important because Lake Winnipeg, actually in Canada, is very well known for its algal blooms. Very often during the summer, algal blooms in the lake. And other research has also shown that the algae in Lake Winnipeg are phosphorus limited. So what determines their growth is the amount of phosphorus that's available. So you can imagine that all this phosphorus that's being retained here, if these reservoirs were not present, all that phosphorus would end up, most of it would end up in Lake Winnipeg. So the algal blooms would be even worse than they are today. Right? So you can think about it from the viewpoint of Lake Winnipeg. This is a good thing, right? Less phosphorus, less algal blooms. Now, of course, what is happening is that if you take Lake Diefenbaker, for instance, in the summer they have algal blooms. So if you manage the reservoir, it's a bad thing because you have an algal bloom in your reservoir, but you're in fact protecting the downstream lake. So again, whether it's a good or a bad thing depends on your viewpoint, if it's reservoir-centric or is it lake-centric. All right, so that was kind of at the regional scale. So at the global scale, this is really how Taylor's thesis started. She wanted a thesis topic, so I said, well, go figure out how much of the river nutrient loads are retained worldwide by dams. Simple question. I mean, you can't get simpler than that in terms of a PhD topic. So she did it, and so her first paper was actually on the global retention of silicon by dams. So that was published in 2014 in Global Biogeochemical Cycles. Then she worked on phosphorus. That was published in 2015 in PNAS. We just finished, or we finished the last revisions on a paper on organic carbon retention. That's actually in Nature Communications. And I have another PhD student now who started on nitrogen. So we'll have all the major nitrogens done. And the final paper, it's not here yet, will be on how the dams are actually changing the ratios of nutrients being delivered to lakes and coastal marine waters worldwide. So what I'll do now is just show one example. An example will be on phosphorus. So, okay, here's your PhD thesis topic. Go figure out how much phosphorus is retained globally by reservoirs, right? So what you do, you go to the literature. Just try to figure out studies where they've actually made budgets for phosphorus, for reservoir phosphorus. That's where the problem is. She could only come up with 155 reservoirs with phosphorus budgets, where we know how much phosphorus comes in, how much phosphorus goes out, the rest is being retained, right? So most of these reservoirs, guess where they are located? Well, they're located in North America or Western Europe. So they're not geographically representative, and also 155 reservoirs is less than 1% of all dam reservoirs worldwide. And we're only talking about the relatively large reservoirs. So statistically, there's no way that these 155 reservoirs could be representative of the whole world. Now, having said that, in part we started this project because other people, I won't provide names here, actually had taken this type of the same data set essentially, calculated the average retention of phosphorus in reservoirs, and multiplied it by all reservoirs in the world. So I said, well, it's kind of fishy. So we redid it, and we have a different number. So how do you now go about this? We have very little data, actual data on retention. But we know a lot about the processes that control what happens to phosphorus in reservoirs, right? Because essentially these processes are the same that happen also in lakes. So you have your inflow, you can have deposition, you can have resuspension, you have diagenesis, you have primary production, we have nitrogen fixation, et cetera, So these processes are fairly well known. So we know a lot about what might happen in the reservoirs. We just have fairly little direct data on phosphorus retention. So the idea here was to combine what we know about the processes with the amount of data we have and try to come up with global estimations. So if you look at this, if you have a single reservoir and you have a lot of data and you have a lot of, the geometry, all the flow, you can actually start modeling all this. And there's some very good reservoir models, hydrodynamics, plus biogeochemistry, plus ecology that are available. You cannot apply this at the global scale because we're dealing with over 7,000 dams reservoir that we want to model. So we have to take a simpler model, or we have to make a simpler model representation. So we use very simple mass balance models where we try to identify the major pools of phosphorus. So we have total dissolved phosphorus, we have particular organic phosphorus, sorbed phosphorus, mineral phosphorus. This is kind of the mineral fraction of the phosphorus that's not really reactive. We need to know how much phosphorus and how much of these different forms of phosphorus are entering a reservoir. We then have to account for these processes, these internal transformation processes or redistribution processes in the reservoir. And then, in principle, we should be able to predict what comes out of the reservoir, not only in terms of total phosphorus, but also the various forms of the phosphorus, right? So how do you do that? Well, first, let's look at this part here. How do we know how much phosphorus enters a reservoir? How do we do that for 6,000, 7,000, up to 10,000 reservoirs worldwide? Well, we use, luckily, there's an existing model, the global news model, the nutrient export from watersheds model, that has been developed to essentially estimate loadings, nutrient loadings from the landscape into rivers, right? And so what it actually does is to predict nutrient yields for carbon, nitrogen, phosphorus, and silicon based on a bunch of drivers: population density, socioeconomic status, climate, hydrology, water management, land use, nutrient management. So these are empirical relationships that tells you if you have a certain watershed with certain characteristics, it predicts how much nutrient loading takes place. I mean, how much nutrient is coming up the landscape. And so you can see for carbon, we have dissolved inorganic carbon, dissolved organic carbon, particulate organic carbon, etc. for also for nitrogen, phosphorus, and silicon. So the approach then is, if you want to know how much nutrients are being loaded to a particular river that then ends up delivering it to a reservoir, you look at the catchment. This is the catchment. These little bars are dams, hypothetical dams in the catchment. So if you take this dam up here, that's receiving nutrient loading from this part of the watershed. This guy is receiving what comes out of this dam, and this part of the watershed, etc., etc. So what you really, it's a very simple calculation. You need to know the yield. Yields are essentially the mass of a given nutrient formed per unit surface area per unit time, and then the catchment area. So the catchment area, again, we get from this this database, this Grandee database. So essentially, you go to that database for a given dam. You can actually, it will give you the size of the watershed, and then the global news model here will give you the yield. So we can calculate for each dam in the database how much nutrient, how much carbon, how much phosphorus, how much nitrogen, how much silicon, and in what different forms is going into the reservoir. All right, so that's the first thing. That's what gets into the reservoir. Then for the processes inside the reservoir, as I said, those are mostly based on what we know about these processes. Most of that information actually comes from studies on lakes. So we can take whatever budgets we have, reservoir budgets we have, and then we essentially merge that with what you know about the transformations of, say, phosphorus in lakes or in reservoirs. That allows us to estimate parameters for our different processes. We represent those by probability distribution functions. And then this, and from our reservoir database, we have then the reservoir parameter ranges, and then we use a Monte Carlo simulation approach, where essentially we take all our reservoirs in the world, we randomly select the parameter values based on these probability distribution functions, we run the model, and we do this over and over and over and over again, right? But what this does is it yields what we call these global relationships. So for phosphorus, for instance, that's what they look like. So here you have the phosphorus retention, the total phosphorus for reactive phosphorus, as a function of the water residence time. Now, the water residence time is a parameter that we know for all of our reservoirs, because the database tells you the volume of the reservoir, the inflow, so you can calculate the water residence time. So we have this information exists. And what we want to know is, of course, the retention efficiency. So 0, no retention, 1, 100% retention. And so what this Monte Carlo simulations then produce is this relationship where you see that the retention of both total and reactive phosphorus tend to increase with the water residence time, which makes sense. The longer the water is in the reservoir, the more time there is to basically remove some of the phosphorus, right? But you also see that for any one of these little bins, you have these huge ranges. Essentially, if you look from here, I could go from 10% to 90% retention. Big uncertainty. So do never use this for any given reservoir. If you have your favorite reservoir somewhere, and you say, well, I want to estimate the total phosphorus retention, this is probably a very bad way to do it, because you're probably going to get the wrong number. If you say, well, that's my mean value, that's probably not going to be what you want. But if you do a global analysis, the more reservoirs you include in your analysis, the more the aggregated result will converge to the mean behavior. And so for a global analysis, this actually ends up, and we've done the calculation, ends up giving you an estimate with a relatively small uncertainty, because it's the statistics of big numbers, basically. So what we can now do with this type of global relationships. We can apply those to all our reservoirs, and we can predict things like this. All right. Simple prediction. What is the reactive phosphorus retention in all the major river basins that flow into the oceans in the year 2000? And we create a map like this. So the blue, well, first of all, when it's white, there's no data. And sometimes it's also you have no data because these are essentially river systems that actually do not flow to the oceans. They flow into the internal continents. So green, not much retention. And as you go to the darker blues, more and more retention. In fact, in the year 2000, the river basin with the most phosphorus retention in reservoirs was the Mississippi River Basin. And so other winners are, for instance, in South America, the Parana, the Zambezi in Africa, for instance. Here you have the Volga, here the Yangtze River or the Ganges. So these were the places where a lot of phosphorus was being retained in reservoirs. Why? Because you have a lot of reservoirs in these river basins. So just for a guess, how many dams do we have in the Mississippi Basin? Any guess? 10, 20? 700. There's 700 reservoirs and dams in. So it's big. It's simply, this is essentially tells you where the dams are, or where the dams were in the year 2000. So now, that's for year 2000. So what about now or in the future? Well, so to make future predictions, you need to know how many more dams will be built. You also need to know how the loadings, nutrient loadings to the rivers are going to change. And so that's another reason why we use this global news model, is because they've actually made estimations for what will happen in terms of nutrient loading in the future using these so-called Millenium assessment scenarios. Nowadays, people don't use scenarios anymore. They talk about storylines, because essentially we have a story about how the future could evolve. Of course, nobody can predict the future, right? No, not too many people predicted that Donald Trump would be president today. So you just come up with a storyline. What if Hillary Clinton would? No. And so they came up with these 4 scenarios: global orchestration, techno-garden, adapting, mosaic, order from saying. And essentially, the storylines are for a more globalized versus a more regionalized world, and for, in terms of environmental management, more reactive. So you try to prevent the problem from developing to a proactive, so proactive to reactive, so proactive before it happens and reactive after it happens. So from an environmental viewpoint, from a viewpoint of loading of nutrients, the global orchestration is the worst, and the adapting mosaic is the best. So now you can take these storylines, predict how your loading is going to change, and then predict how that's going to affect retention, also taking into account the fact that we're building more and more dams. So this is, for instance, a map that shows by how much the reactive phosphorus retention will increase between the year 2000 and the year 2030. And so again, now if you go to the Mississippi, where we had the most retention in 2000, it's completely blank because there's no more reservoirs being built, and because the loading is not increasing anymore because of measures that have been taken to prevent increased nutrient loading to the river. What you see now is that the red spots are, for instance, again, the Amazon basin here in Brazil, primarily because of the building of new dams. The Zaire or the Congo River here, there's a big dam being built right now somewhere over here in the Zaire. There's still a lot of, here you don't see the red spot because it's covered by the dots are again the dams that are being built under construction. You see a red spot here for the Ganges, you have the Yangtze, and here the Mekong, you hardly see it. So to present it slightly different, so if you look at where we have the largest increase in phosphorus retention from 2000 to 2030, these are the winners. Yangtze River first, followed by the Mekong, the Amazon, the Ganges, and the Salween. And the reason is simple: all these new dams are being built. So just these numbers are staggering. If you take, for instance, the Ganges Basin, 400 new dams are or will be built by 2030. Right? Okay, so what does that do then? Well, that's the retention. But in fact, if you're managing a reservoir, that's your problem, because that's related to internal loading in your reservoir. Let's look at it from a different viewpoint. Let's look at how these dams are basically modifying the export of phosphorus to the coastal zone, because that's where we have these algal blooms, these big coastal algal blooms. And so what I'm showing here are the change in the export of total phosphorus to the coastal zone for the different continents relative to the 1970 export. So 1970, that's our baseline. So for instance, if you take Europe, you can see that in 2000, we had less export of phosphorus to the coastal zone of Europe relative to 1970. This mainly is due to the legislation that banned phosphate from detergents. So phosphate was taken out of detergents that reduced the point sources of phosphorus to rivers, and basically we had this drop in phosphorus. Don't see very much change in North America, a little bit of a drop in South America. Look here for Asia, relative to 1970, a huge increase by the year 2000 of the export of phosphorus, simply because of increased use of detergent and increased use of fertilizers for agricultural production. So now we go to our projections for 2030. So the first two, the green ones, are if we assume that between 2000 and 2030 we don't build any new dams. It's of course wrong, because we are building dams. But if the number of dams would have been kept constant from 2000 until 2030, by how much would the phosphorus increase or decrease? AM stands for adapting mosaic, so that's that this scenario, versus the GO, which is the global orchestration scenario. And so if you see again for Europe, things are about the same. It increases slightly for North America. In fact, most of these increases in Canada, not in the US. But again, if you take Asia, you see huge increases in the amount of phosphorus flowing into the coastal zone, again, because of growing population, more fertilizers, more waste, water being produced, etc., etc. So now we're building our dams. We say, okay, well, between 2000 and 2030, we're building all these dams that Christian Zarfel put in her database. And if you look for Asia, for instance, you see that, in fact, that brings down the predictions to about the 2000 level. So what we have here is that the building of new dams is just offsetting the increased loading of phosphorus to the river system. If you look, for instance, for Europe, it would actually lead to an even larger decrease. And for the North America, you see a reversal here, where instead of increasing the export, we actually decrease the export. Right? So that looks pretty good. You could say, well, that's actually, for the coastal ecosystems, a good thing, because essentially our dams are retaining the phosphorus up on the continents. Now, that's for total phosphorus. So if you look at reactive phosphorus, it's actually not as good. Remember, reactive phosphorus is the bioavailable phosphorus. So that's actually the phosphorus we should be worried about. So if we just focus here on Asia with the same thing, from 1970 to 2000, it increases. From 2000 to 2030, with no new dams, it increases to this level and this level for the two Millenium scenarios. If we now build the dams, we bring it down again, but we don't bring it down to the 2000 level. So the prediction here is that even with the dam building, more reactive phosphorus will end up in the coastal zone in Asia. So we would expect even more harmful algal blooms to take place in the coming decades. All right? Okay, so very quickly, just go over this before I get to the conclusions. So we've also tried to estimate how much organic carbon is retained in reservoirs. In other words, that's the carbon that does not reach the oceans. Again, our time points are 1970, 2000, 2030, and 2050. So if you first look at these little pie charts here. In this pie chart, the light green is actually the fraction of the organic carbon loaded to rivers that actually has to pass through a reservoir. And so again, it shows you that from 1970 to 2000 to 2030, the amount of organic phosphorus that is actually going to have to or end up in a reservoir or go through a dam is actually increasing because the number of dams are increasing. The only thing I want to emphasize on this graph is if you go from 1970, this is the total organic carbon entering all reservoirs worldwide. In 2000, it's more. That is mainly because we have more dams in 2000 than we had in 1970. It increases again from 2000 to 2030 because we still will have more dams. The red arrows correspond to actually primary production in the reservoirs, so driven by the nutrient input in the reservoirs. What is also shown here is this yellow, this brownish arrow. That's actually the mineralization of buried organic matter. So when you build a dam, you flood part of the valley, so a lot of the biomass and the soil organic carbon will then also be available for mineralization. So you see that, for instance, if we take, for instance, 2000, it's a relatively small arrow. That's because in 2000, the average age of the dams was relatively long. They had been built in the 1950s, 1960s, 1970s. If you now go to 2030, you see a much bigger arrow here because these are all very new dams. So we've flooded a lot of biomass. So in other words, this is, of course, CO2 that goes to the atmosphere. So the age of the dams will, of course, have a big effect on this prediction. Bottom line is that by 2030, about 20% of the organic carbon carried by rivers to the ocean will be eliminated by in-reservoir burial, up here, or by respiration, by being expulsed as CO2. So again, these are big numbers. So again, indicating that we will modify the carbon cycle. We are modifying the carbon cycle by building those dams. All right, so take-home messages. So river damming is one of the major anthropogenic modifications of the continental cycles of water, carbon, and nutrients. Dams create new biogeochemical reactors along the river continuum. So these reservoirs, a lot of is going to take place. And in fact, this is actually, a plea for more studies on reservoirs. Because, as I showed you, for phosphorus, we only found about 150 studies that gave us a complete picture of the phosphorus cycle in reservoirs. If you do the same analysis for natural lakes, you'll find not zillions, but a lot of studies. So in the past, the community has been kind of doing a lot of research on natural lakes as compared to reservoirs. But these reservoirs are new anthropogenic environments. There are a lot of them. In fact, if you exclude all the very, very big lakes, so the Great Lakes, Lake Baikal, Lake Victoria, etc., the amount of the volume of water stored in reservoirs, actually, it's still smaller than the total amount of water stored in the lakes, but it's starting to be on the same order of magnitude. So we need more studies on what's happening in these reservoirs. Processes in reservoirs decouple riverine nutrient fluxes, and in general, this is kind of a general rule, it's not going to be true for every reservoir, is that typically phosphorus is more retained than nitrogen, which will promote phosphorus limitations in rivers, lakes, and coastal zones. In fact, there's quite a few studies out now that show that coastal environments that were nitrogen limited are now switching to phosphorus limitation. And part of the reason, not the entire reason, but part of the reason could be this damming of rivers. Despite the ongoing surge in dam construction, export of reactive phosphorus, so the bioavailable fraction, to global coastal zone will likely continue to rise in the future. So we can expect that this problem of coastal harmful algal blooms is not going to go away anytime soon. 20% of organic carbon loading to river systems is eliminated in dam reservoirs. Anthropogenic nutrient loading plus damming are causing river systems to become more autotrophic with time. I didn't really elaborate on that, but essentially, a lot of the primary production that used to take place in lakes and in the coastal zone is now taking place in these reservoirs. So we're moving primary production up the rivers. And over the next decades, the largest change in riverine nutrient cycling by damming will take place in Asia and South America. Right. And that's it. From Canada, you have to have a beaver somewhere. So for phosphorus, for instance, retention in lakes is typically much larger than in the reservoirs. And that's because a reservoir is not really a lake. A reservoir is something between a river and a lake. And the average water residence time in most reservoirs is less than 1 year. So there's much more time. In a typical lake, there's much more time to have it go over and accumulating the sediment. So it's not as efficient a trap as a natural lake. So if you, for instance, take all the phosphorus entering the Great Lakes, and you look at what comes out in the St. Lawrence, that's a very small fraction, because most of it gets retained in the lake. Right? So it's really, I mean, the way you can think about lakes, about reservoirs is, it's between the two endpoints, between a real fluvial system and a lentic system. That's a good question. And that's something it's a question I get all the time. Could we start mining reservoirs for phosphorus? The reactive phosphorus is essentially when we talk about reactive phosphorus, as long as it's reactive, it can be regenerated. But early diagenic processes will transform that reactive phosphorus into unreactive phosphorus. So once it's buried, it will ultimately become fairly immobile. No, yeah. It's essentially no, not so much. Yeah. But the recovery is an interesting question. And since we're going to run out of phosphorus before we run out of fossil fuels, it might be an issue. And in fact, in some cases, I know of projects in India where smaller ponds, so they're not really big reservoirs, are actually used to receive agricultural runoff, and then to essentially have all the settling done, and then you reuse that on the fields. That's a very nice way of recycling the nutrients, so it's not just the phosphorus, it's the nitrogen and everything else. Yes, yeah. So those are the two effects. It's increased loading, which is mostly driven by more people, and that's included in these Millennium assessment scenarios. So the population growth is included in that. So that's taken into account. Now, the Millennium ecosystem assessments were created about 5-6 years ago. So a lot of people say they're outdated. So we have to redo those. We use those because essentially global news projections, these Millennium ecosystem scenarios were built into the projections of the global news. So they did the work for us. They told us, well, in any catchment, taking into account socioeconomic changes, taking into account climate change, also climate change predictions, this is how the loadings are going to change. So we take into account both the changing number of dams and the changes in population density. Yep. Yeah, because we express those in moles also. The units are different, but so yeah, if you think about it, for the organic carbon, the estimate is that the whole loading to the inner estuaries globally is about 10 petagrams. And then there's about half of it that gets eliminated in the estuarine system that never reaches the open ocean. So we have, of course, the coastal zone is an extensive biogeochemical reactor where this will take place. What we're saying is that if you didn't have all these reservoirs, you would have 20% more coming in. So big reservoirs retain more phosphorus, or they retain more nutrients. It's big, essentially because the large reservoirs typically also have the longer residence times. So those are these big, like Powell Lake, for instance. It's not only that they have longer residence time, they also tend to be very long. And in fact, what we saw in Lake Diefenbaker, which is one of these very long reservoirs, most of the deposition takes place when the river just enters the reservoir. So there's a depot center there. And that's where a lot of the accumulation takes place. So it's not near the dam. It's actually upstream that most of the precipitation takes place. Yes. Well, certainly if you want to run your Earth system model, say, to make predictions of CO2 emissions from reservoirs, that will be the mineralization processes are one of the dominant ones. And for the nutrients, well, in fact, our organic carbon model is driven by the nutrients because the nutrients are controlling the photosynthetic uptake of carbon in the reservoirs. So the two are coupled, they're not independent from each other. But for the nutrients, I would say the main is to have better estimates of the loadings to the rivers. It's actually the inputs that are probably the least constrained. Because these loadings, the way the global news does it, is their yields, ultimately the only validation data that they have is what comes out at the river mouth. So a lot can happen in your watershed that you don't capture properly. The other thing is that for reservoirs, there is actually a lot of data out there, but it's controlled by the company who's running the hydropower generation, etc. So these companies are very, very resistant in providing information. So just going a little bit upstream and measuring what's coming down would be actually. So that's certainly that's the biggest unknown. So a lot of the absolute numbers we come up with are essentially determined by what the global news tells us is the input to the reservoirs. There's a lot of uncertainty with those loadings. So I think that is the biggest unknown that we have for the moment. Once it's in the reservoir, the parameterization of respiration processes, burial processes, that is actually far better known because we have a much larger body of information. In fact, mostly from studies it takes, but it's the inputs to the reservoirs. Yeah, but that's the Lake Diefenbaker study. I mean, we have beautiful studies because there's the reservoir intake, so where the river comes in, there's a monitoring station, there's monitoring stations downstream, because Lake Diefenbaker is basically all that water that provides water to a system of overlay to some of the biggest cities in Saskatchewan. Big cities in Saskatchewan is not that big. Still. So there's a lot of data, and that is publicly available data. Well, publicly available, you still have to, it's still in reports that you have to find in somebody's drawer. Individual reservoirs, you can do that. So for Lake Diefenbaker, there's some very nice data. In fact, sometimes Lake Diefenbaker is covered with ice, then nothing's happening. We have a latitudinal correction in our model, so we account for very roughly the temperature. So also the amount of daylight. So that we've scaled our photosynthetic photosynthesis according to latitude. So there's a correction there. Any individual reservoir, much more detailed representations. Yes, but what we would need is to couple our organic carbon also to a DIC model, and then obviously stratification becomes an issue. The way we've included stratification for the moment is very, very simplistic. No, we do, because essentially, if you have stratification, you have more release of the. But as I said, it's very simplified because we essentially parameterize it depending on the depth. The hypothesis: the deeper the reservoir, the more chances for stratification. So it's kind of the width-depth ratio that we put in there, which is not ideal because there's other things that will control stratification. So as I said, don't use this for any individual reservoir. Great. I mean, you can be wrong for any individual reservoir, but if you put them all together, then you get the right answer. Yes, but it's amazing how much of all these other parameters actually scale to the residence time. And it's at the very basic level is, if things are flushing through, not much is going to happen. If water is going to stay there for quite a while, and algae can do with their thing, and the sediment can settle out. So all these, like for instance, the burial efficiency, photosynthetic efficiency, all these scale to the water residence time in this very simplistic representation. Because remember, all the physics is essentially parameterized to the water residence time, and all the chemistry is the transformation between these different ones. If at some point you go to a more complex model, you will see that that's going to break down. So in other words, the relationship with water residence time, to a certain extent, is also a reflection of the model structure that we're using, because we're putting all the physics